So I
Go
think we
ahead.
can get started. There's still people coming in, but it's all right. They'll catch up. So good morning. We are very happy to be here with Guillaume. I think it's been a while since the last webinar we did together. So today we are going to speak about motor drives and especially how modulation strategies impact the motor drives. So my name is JMAG-RT and I am the lead developer of Simba. And I'm with Guillaume, our power electronics expert. So we will start for those of you who doesn't know Simba. We'll start with a quick overview of what is Simba. Then we'll cover relatively quickly the latest features of version 24.05 that we are currently releasing, actually as we speak. And then we'll actually start the part on the modulation strategies for motor drives and how to use Simba for that. And finally, we'll have a little bit of time for question and answers. We expect the webinar length in total to be around 30 minutes. Okay, so what is Simba? So first, Simba is a power electronics and motor drives simulation software. It can basically everywhere you have power converters, you can use Simba. So from EVs to transportation, energy systems, everywhere you have a power converter, you have to design a power converter, you can design Simba. It can be used for a lot of different types of applications. You can select and optimize the technology, you can run power quality analysis, you can look at thermals and efficiencies as we will do today, and many other things. It can also be used for control design, where you can develop C code right into Simba. You can look at the stability of the converter. You can, of course, simulate complete motor drives. And in Simba, you can also run detailed analysis, a little bit like what you are used to do in SPICE, where you can look at detailed transients, EMI, and interaction with PCV parasitics, and so on. There is three main aspects of Simba that we would like to show to you. The first one is inside Simba, we have different model of switches and different levels of modeling. So here, this is a very simple buck converter, and we look at VDS on our MOSFET. And we can see that we superimpose different waveforms. Actually, the different simulation, the three simulations that we have, comes from different switch models. So first we have the ideal model, where basically the switch is either a pure short circuit when it's closed or a pure open circuit when it's open. And we can use that for like system level simulation. And we can also use that to run thermal analysis with lookup table, as we will do today. But if you look at the green curve, in Simba, you can also run detailed semiconductor model. You can create your own semiconductor model in Simba, or you can import SPICE model in Simba. And here, you will be able to look at detailed switching transient, have more physics-based loss analysis, and you can study gate drivers, EMIs, and things like this. So that was the first main feature of Simba that I wanted to introduce. The second one is the capability of Simba to be used for motor drives simulation. Of course, that's the topic of today, and Guillaume will go in much more details. But in this case, so this is a simple PMSM with a three-phase inverter. And in this case here, the switch is ideal, and we use thermal lookup table to estimate the conduction and switching losses. And from those losses, we can actually calculate the efficiency of the entire motor drives. And this is the kind of study we can do, where we can have efficiency map of the motor drive, of the inverters, and study the losses into the entire system. And the last feature that I wanted to share with you is the capability of Simba that's pretty unique, to be entirely automated. Simba can be used as a native Python script module. And that's actually a game changer. And that's probably the one, maybe the best feature of Simba, is you can actually do everything using scripting. And in this case here, we use kind of brute force to find the best parameters of this LLC converter. And just to give you an idea, here we run about 10,000 simulations with different parameter sets. And because in Simba, we can run simulations in parallel very easily, you can see it's like a few lines of code. This takes on my computer less than 10 minutes. So less than 10 minutes to run 10,000 simulation of an LLC converter. So this is really game changing. So that was a very quick intro to Simba for those of you that are not familiar with the tool. Now I would like to cover the new features that we are currently introducing with 2405. The first one is we are introducing a new magnetic library. So in previous version of Simba, we had ideal and non-ideal transformers, we had ideal and saturable inductors, but now we add the capability to use the electromagnetic analogy to build magnetic circuits inside the tool. That was very highly requested by some of our users. So for instance, here we have a simple transformer. So this is the interface of Simba. For those of you that are not familiar with the tool, that's very clean and very simple to use. So in blue, we have the electrical circuits. In green, we have the controller. And in kind of purple now, we have the magnetic circuits. So this is modeling simple flyback transformers where we have two windings, where we specify the number of turns. We have a linear core where we set the relative permeability and the geometry, and the transformer air gap. And this is helpful for different things. It can be used to model kind of non-standard transformer topology, like zigzag transformer, for instance, and to build, all magnetic circuits that you want. So I can run the simulation. We can look at, the output voltage, for instance, this one. We can look at the flux rate in the transformer. And yeah, that's pretty much it. So, something to note is right now we support in the magnetic circuit only linear models, but we are actually working on non-linear models, the capability to model saturation in the magnetic circuits and also hysteresis and all the non-linearities that we'll find in magnetic circuit. The second feature that I wanted to share that was also very highly requested by our users is the capability to read and simulate SPICE netlist. So we have a new model in our library that's called SPICE netlist. And the SPICE netlist can be used a little bit like our C-code model. So you click on the edit button, and here you can directly inside Simba write SPICE code. And what is important to remember, and this is not like a SPICE solver that runs in parallel of Simba. The SPICE netlist and the SPICE models runs inside Simba. There is for the solver, there is no difference between a SPICE model and another Simba model. So there is no kind of co-simulation, there is no delay. Everything will iterate simultaneously. So for convergence, we won't have any issue. This and the SPICE netlist. So this is a very simple RLC circuit. And you can specify node names, like for instance, this node here, C4 underscore 1, and you can actually connect to the Simba circuit. So the SPICE netlist is not in a sandbox. Is in a sandbox. You can actually interconnect it with your circuits, and this can be used for many different things. It can be used first to import model from SPICE. So this is usually like integrated circuit models. Also, and that's actually the reason why we have developed that, is some of our customers wanted to import parasitics parasitics values that are calculated by tools like Q3D, so PCB parasitics. And basically, you can import that in Simba to run like detailed EMI analysis. And you can also use it to import semiconductor models from semiconductor vendor. And we are currently working with some of the major semiconductor manufacturers to make sure that all the models that we import work correctly and are validated inside Simba. We have added a new feature for scope compression. So basically that reduced the memory footprint of Simba. That was an issue that we had in previous version, where if you run like a very heavy model for a very long time, you can have literally gigabytes of scope data. And with this scope compression, we can reduce in average by 80%. So that makes the simulation faster, that reduce the risk of crash of the simulation. So, so here you can see in the flyback converter that when we compress the scope, we just keep the points that carry information, and we remove all the points that are not relevant. We have added the capability, this is more on the user interface side. We have added the capability to move and show the parameter values of the components. So that was something that was missing in the previous version of Simba that we now support. You can change the font, you can set the color if you want to. And also we have added Python auto-completion. So if you use the Python API now with 24.05, you can actually stop to type, and like what you see here, it will autocomplete. So you can code like literally you are in 2024 and not in 1998. Okay, so that's the main feature of 24.05. Of course, there is a lot more that we cannot cover today. We try to release version of Simba quite on a very regular basis, every 3-4 months. So yeah, if you're a Simba user, I really encourage you to try this new release. Only good things. So that was a quick intro about Simba and the new features of 24.05. If you have any questions, feel free to ask them. But now it's time to get the plat de résistance with Guillaume and the motor drive analysis. Thank you all.
Well, thank you, Emmanuel, for this great review of these last features of Simba. It's still well impressive, you know. Even if I'm in the boat, it's very impressive. Okay, so I'm going to share my screen. This one. Okay, here we are. Good. So now, yeah, let's talk about this issue that a lot of power electronics engineers have to cope with, which deals with the evaluation of the losses of both inverter and motor, and especially if it deals with different operation points and different modulation strategies. So today, the current solution to solve this kind of issue is to use separate tools, which means that first tool for such as power electronics simulation software to evaluate the losses in the inverter, and a second tool or analytical expressions in order to evaluate the losses in the model. So today, we are going to propose a combined solution of Simba and a JMAG-RT model, which has been extracted from JMAG, the finite element modeling software, in order to get the global losses of the system. Okay. But before keeping on, let me ask you some question. I'm going to launch a short poll in order to get your feedbacks and your fields. Okay, so in your multi-drive application, so here is my first question. So what is the typical voltage level of the multi-drive you design? So you can see that on the screen, you've got several questions about this voltage level. Okay, so here, okay, so we've got a good sharing between low voltage and medium voltage. Oh, few of them are designing very interesting drive up to 3 kilovolts. Okay, that's interesting. Okay, so yeah, that's perfectly understandable. The main part is dealing with low voltage, let's say a little bit lower than 1 kilovolts. Okay, great. Thanks a lot for this. And so now I'm going to ask you a second question, which is this one. What is the inverter topology you're dealing with most of the time? Is it a classical 2-level, or are you dealing with, okay, 3-level, okay, NPC? Okay, some older people are dealing with older multi-level inverter topology. That's quite interesting. Okay, and by the way, I take the opportunity to warn you that after this webinar, when the webinar ends, you will propose to answer to a survey in order to say what you liked in this webinar, what you disliked, what you would like to improve. This helps us a lot. Okay, so yeah, thanks a lot. So the main part is dealing with 2-level, but yeah, a good proportion is also dealing with 12-level topology. But thanks a lot for this sharing. So so today, what we are going to do now. So here's the approach we are going to consider in order to evaluate the losses of the inverter and the model. So the power switch model will be associated with a thermal description, whereas the motor model will be associated with a JMAG-RT model. And we are going to evaluate the influence of different modulation strategies, 3 modulation strategies in this example. And then different switching frequencies and 2 operating points, one at high torque, low speed, and the second one at high speed, low torque. So the first step is to build the global circuits in Simba. So here you can see that we've got the power stage in blue, the control stage in green, and the thermal stage in yellow. And this design is duplicated 3 times, once for each modulation strategy. So here, if we have a look a little bit at these modulation strategies, here the main objective is to increase the DC voltage utilization or to reduce the switching losses. And this is done with the insertion of a 0 sequence reference in the modulation scheme, which can be done only if the neutral point N here is floating. That's to say, not connected to the ground here, which is usually the case for multi-drive application. And here in this example, we are going to consider 3 modulation strategies. The first one, which is the most classical assigned PWM, And then the space vector, well, it's a space vector-like, actually, because it's a carrier-based, where the zero sequence reference is a triangular waveform which has been inserted. And the last one, which is this discontinuous PWM, which aims to reduce the switching losses when the current is at its maximum. So here again, let me ask you a small question about the typical modulation strategy you're using. So here again, you will have this. Okay, so yeah, most of you are using SVM, space vector modulation, or sine PWM modulation, and a few of them. Yeah, that's very interesting. Okay, let's close the poll. So maybe you can see now, I'm trying to share the results. Can you see them? Emmanuel, can you see the results which are displayed in your screen?
Not yet.
Not yet.
Me, yes, but I don't know if everybody can see them.
And if I share my screen like that, okay, so you can see that I would say 60% of you are using space vector modulation, whereas 30% are using sine modulation. Okay, so here, which means that the three modulation strategies we are going to consider are quite relevant. So here again. So now let's go back to the global design here and have a look at this power switch model. So as I said, this power switch model is associated with the thermal description. Here we have considered this silicon carbide MOSFET from Wolfspeed. And with this thermal description, we are able to define conduction losses, energy switching energies, but also a circuit for the thermal impedance. Let's go back to the main circuits in order to have a look at the JMAG-RT model for the motor. So this model can be extracted from JMAG Designer or from JMAG Express. Here are the characteristics of the motor which have been considered in this example with DC voltage of 600 volts and the maximum power in the mechanical field of 80 kilowatts. So now the first step is to load this JMAG-RT model into Simba. And this is very easy to do this. We just enter the model and then specify the RTT file, which has been extracted from JMAG Designer or JMAG Express. So what do we have in this JMAG-RT model? So as I said quite quickly, we have lookup tables which allows us to define the total flux, the inductor, but also the torque and the iron lysis, which depend on the current vector amplitude, but also its angle and the mechanical position of the rotor. And about the losses, which is interesting for us today, we have a first step with a base model, which makes possible to get an accurate waveform, which means that here we've got the inductor of the motor, which is based on the lookup table, which depends on the current, but also on the motor position, as I said. And then we have the iron losses, which also depends on a hybrid approach with a lookup table and analytical expression. It's also possible to consider AC copper losses, even if it hasn't been considered in this example today. And it's extracted with an analytical model based on geometry. All these details of this method, which is quite very interesting, are detailed in this publication and from ECC conference in 2022. So now the last step before getting results is about writing the Python script. So here, of course, we load Simba module, the multiprocessing package in order to perform parallel computing, 2 operating points, and different modulation strategies and switching frequencies. Of course, we run the simulation method in order to run the Simba model and to get the results. And finally, we're able to get the first results. So, for example, here we've got the current waveform through the motor, and we clearly see here the influence of the switching frequency on the current ripple. So it's quite clear that when the switching frequency increases, the current ripple through the motor decreases. And we can also see the influence of the switching frequency on the junction temperature. So here again, we can see that increasing the switching frequency will lead to an increase of the junction temperature, but also on the temperature ripple of the MOSFET, which is very, very important for the reliability of this kind of device. But the most interesting part here is to sum up all the results of all the combinations. So that's what we have. That's what we have made here for the first operating point at high torque, low speed, and for the first modulation strategy, the sine wave. And here we have displayed the different types of load or loss from the connection losses in the MOSFET, switching losses in the MOSFET, and the motor losses, such as the copper losses and iron losses. So here it's we can clearly see that the increase of the switching frequency increases the loss, the switching losses in the MOSFET. For the other losses, they are more or less constants in this case. We can do the same thing for the other modulation strategy, of course, such as here the space vector modulation strategy, which will give more or less same results. It's actually it's a little bit better. And also for the last modulation strategy gets to say the discontinuous PWM. And here it's quite interesting to note that these modulation strategies can allow the user to minimize the effect of the increasing of the switching frequency. Indeed, here you can see that at the highest switching frequency, at 60 kilohertz here, this is not a big deal of increasing the switching losses in the MOSFETs. For the second operation point, it will be quite different, as the iron losses are quite important, and I would say they are a little bit in competition with the switching losses of the MOSFET, which means that's not obvious that increasing the switching frequency will lead to a decrease or to a lead of an increasing of the losses. Indeed, that's what we can see here, that when the switching frequency increases, it will decrease the iron losses in the motor, as the current amplitude, the current ripple through the motor at a high frequency will decrease, and thus will lead to a decreasing of the iron losses. So here we can see that there is a kind of trade-off, okay, to get with the modulation strategy and also the switching frequency to get a good sharing between the losses in the inverter and with the switching losses of the MOSFET and the iron losses of the motor. And in this case, the last modulation strategy with the discontinuous one can be a good choice. which leads to a kind of conclusion, discussion for these two operation points. So, well, first, it seems that, of course, the space vector PWM is always a little bit better than the sign PWM because it allows the user to use lower modulation index. But what is quite interesting is that for operation points with high torque, low speed, it's quite interesting to decrease the switching frequency as much as possible to decrease the switching losses, or to use discontinuous modulation strategies in order to keep a high switching frequency. But for high speed and low torque operation point, it's quite different. Then here there is it can be very interesting to increase the switching frequency to decrease the iron losses in the motor, and this can be also coupled with the modulation strategy of the discontinuous one in order to decrease the switching losses in the MOSFETs as well. So yeah, that's the kind of one falls to die. Well, I hope so. that is kind of great use case, according to me, that we can do in Simba with an isolation of the JMAG-RT model in order to get these losses, the losses of all the system. Yeah, so yeah, that's all for me, Emmanuel. And if our attendees have any question, it will be a pleasure to try to answer them.
Thank you very much. Guillaume, I do have one question. Are the scripts that you wrote and the model available?
Oh yeah, thanks a lot for this. All these examples. Thank you, my name Emmanuel, for reminding me this. So here, if you go to the technical resources we have developed, here you can find some tutorials, examples which are mainly used with the desktop application, and also I would say examples which use the Python library of Simba. So here we've got a bit more than 40 examples, and the example I presented today is this one, the fourth, which deals with the modulation strategies of a multi-drive inverter. You can click here on this, and you will have a short description, of this model. You can recognize the circuit I've just shown you. And here at the top of this file, you can download the Python scripts for simulating, the Python script for plotting the results, the Simba model, also the JMAG-RT model, which has been created, as well as the Python library requirements. And here you've got a short presentation of what has been done and of the results here I've just presented you. And do not hesitate to download them, try to use them, to send us your feedback. It's very interesting for us to improve this kind of use case.
Just I want to add a little something. So all those examples and all the codes, it's actually on an open source GitHub repository. So if you prefer, you can also clone this repository, and you have access directly to all the examples. We have a question from Adam.
Yep.
Guillaume, first question. What about the impact of the modulation strategy on the harmonics content and current ripple?
Yes. Thanks a lot for this question, because this is of course we could have plot, we can plot the harmonics content of of the different modulation strategies, because this is the whole point. This is because these different modulation strategies lead to different harmonic contents and different current ripples, which leads to different iron losses in the motor. So here I've just plotted the results, but of course it's possible to plot to perform some FFT, and in order to have a look at the THD, for example, yeah, in order to see if you will be okay with, for example, your system requirements.
Thank you, Guillaume.
Yep.
Question from Marco. I will get this one. I would like to try Simba. Where can I download it? That's pretty simple. You just go on simba.io, you create an account, and then you have a button to request a trial license. And once you have an account created, you can download Simba desktop from the user interface. And if you want to use a Python module, it's just like a Python package that you can download with pip, for instance. Other question from Sabir. Okay, I will get this one as well. Is there any option to integrate Simba with MATLAB for system level simulation and automatic code generation? Yes, there are different ways to integrate Simba with MATLAB. One of them is to, yeah, I think it's what you want to do, is to generate code from MATLAB. So basically the code generated in MATLAB, the C code, you can import it in Simba, either as a source code or either as a compiled library. So that's one integration that exists. The other is actually MATLAB is compatible with Python. So you can write M scripts and call our Simba Python module directly from MATLAB. So I hope that answers your question, Sabir. Let me know if it's not the case. Question from Pao, I think that will be for you, Guillaume.
Exactly. So your question is in low frequency applications where the switching frequency is below 16 kilohertz. Your question is does the DPWM, that's to say the discontinuous modulation, make a big difference in reducing losses? And what's the counterpart of these discontinuous modulation strategies? Well, I would say that the first answer is that we usually don't know before running a simulation and a study. So in my experience, for this kind of low switching frequency, no, it doesn't make a big difference, but we don't know. For example, I had an experience, some examples with medium voltage drive applications where the switching frequency was quite low, and here in this case, it made a big difference. So I would say it depends, and especially it depends on the motor. If the motor can be sensitive to the harmonic content of his feeding currents. So yeah, this is answer to the second part of your question. So what is the counterpart of this DPWM? Is usually as the switching frequency, as we clamped, the reference, and then as the three-phase motor inverter doesn't switch anymore for high current, then it's a little bit where it's that's not that good for the harmonic content of the motor, and sometimes it can lead to higher losses in the motor. So that's the drawback of this discontinuous PWM, and that's why the power electronics have to look at.
Thank you, Guillaume. Another question from Philippe, I think, for you.
Oh, yeah. And I'm going to, so Philip, I'm very pleased to learn that you wrote, that you're writing a test, that you wrote this thesis on this topic. I'm going to share my screen in order to show you what we have done as a validation with Simba and JMAG-RT. So here, this is with the Python example, and we've got comparison JMAG-RT with Simba. here it is. So here we have just made a comparison of the waveform in JMAG-RT and JMAG with ideal current waveforms, and we've got this. So yeah, this is our first validation for the JMAG-RT model. And well, of course, we can see if you're interested, you can see that to check the losses between JMAG and the JMAG-RT model. And the second part of the question was about sorry, because I didn't see the second part of the question. It seems to me that not modeling AC couple losses in such a simulation is out an important part of switching frequency dependent losses. Yes, yeah, that's right. Yeah. Sometimes it can be the case that the next step of such a use case will be to integrate the AC couple losses, because for high switching frequencies, these losses can be important and cannot be neglected. So the use we presented today in this context can be considered as a first step.
Thank you, Guillaume. A question from Ravi. How much in detail we can simulate the EMI, EMC performance? Does it contain various EMI, EMC standards plotted for verification? So I will answer this one. Yeah, we can get in relatively good detail. I would say a little bit similar to SPICE, will just be faster than SPICE. So that means that we have detailed semiconductor model, we can have filters like common mode shock, we can simulate PCB parasitics. For the EMI, EMC standards, we don't have those directly in the user interface, but we have some examples in Python where we actually run a Python script and we export the waveforms through an FFT, FFTs, and we compare with EMI standard. So that's that. Question from Philip. We have actually a lot of questions. I don't know if we'll be able to answer all of them. I'm sorry, but let's go ahead. Question from Philip. Did you calculate magnet loss if a PMSM was simulated? Those losses are highly dependent on the switching frequency and can increase the temperature in the rotor. The losses are not spatially resolved, right?
So, yeah. I think that's I'm not sure because I'm not a JMAG expert, but I think that these losses are taken into account in the magnetic losses and the iron losses in Simba. And if I remember properly, they can be spatially resolved. I've seen this in the option of they are. I'm going to share my screen once again. Yeah, so here we are. So here I dig into the parameters of the JMAG motor, and you can see that here we've got different options in order to select the accuracy of this JMAG-RT model. And here we've got consideration of the spatial harmonic differential. But if I don't know if the magnetic losses are considered. So if you send us your contact, we will be able to answer you afterwards.
Thank you, Guillaume. A question from Anonymous. Can you show demonstration using Simba? Probably we won't have time, but if you look in the YouTube channel, you will find a lot of video about using Simba. And if you want a trial or if you want a demo from us, just create an account and you can contact us and we'll be happy to arrange that for you, Mr. Anonymous. Question from Firman. It would be nice to show also the torque ripple for different modulation strategies. You want to get that, Guillaume?
Oh yeah, the answer is quite the answer is quite easy. That's right. That's right. You're right. So definitely. I know this for next time.
A question from Tobias. Is there an agreement for the acquisition of license for universities? Yes, actually, we offer free Simba licenses for education. So if you are part of a university and you want to use Simba for education and education only, you can get free Simba license. If it's for research, we have like a special highly discounted prices for Simba. Question from Sabir. How does the simulation results, like power loss, compare to the real life test data? Have you performed any hardware testing to back the simulation results? The answer is yes, but not directly. So for instance, for the losses in the motor, Jessel, the company that developed JMAG and that built the JMAG-RT, they have test benches. They have like a lot of different motors, and they have validated the different type of losses of the model and the accuracy of the model. For the losses of the semiconductors, so the inverter losses, we take whatever data that comes from the manufacturer. So for instance, here, Guillaume used a semiconductor from Wolfspeed. The Wolfspeed, they provide, like in the datasheet, they provide energy curves and VI curves for the diodes. So they provide those curves in a digital format that's called the thermal data description file, and we use those data from the manufacturer. So basically, those data needs to be good. Otherwise, the simulation that we do are useless. Garbage in, garbage out. So I hope that answers your question, Sabir. Question from JM. What about PFC impact in the efficiency? Is it possible to evaluate?
So
you want to get that, Guillaume?
Yeah, I can answer this question. So I'm assuming that you're talking about the front end, that is say the passive or active front end, in order to generate the decibels voltage. So yeah, of course that's possible to design in Simba this rectifier with a diode rectifier or with an active rectifier, and then to associate these bar switches with thermal description of the MOSFET, and then to get the losses in the rectifier, of course.
Thank you. Question from Ravi. What can we expect the difference in simulation results between PSpice and Simba if we are simulating a gate driver circuit in details with parasitic involved? Well, this is a little bit subjective, and we have not performed any direct comparison with PSpice. What I can expect is two things. The first one is I find it, and again, it's a little bit subjective, and maybe so you need to take that with a grain of salt, but I think that in most of the SPICE results, the simulation is extremely sensitive to the simulation settings. If you change a little bit one of the relative tolerance, or if you change the integration method or whatever, the simulation results will get different, and it's very hard to know which waveform is true and which waveform is wrong. In Simba, we don't have this issue because we have virtually almost no simulation parameters. That's first thing. Then I expect, but again, we have not tested, so it's just an hypothesis that we will be much faster than the other SPICE tools, because the method we use to solve the circuits is different. So I hope that answers your question, Ravi, but if you would like to do a benchmark, we'll be pleased to work with you. We will be pleased to work with you on this. Question from please go ahead.
Yeah, the question from Adam Siplam. I just sent you in the chat the DOEI link to the paper, which is mentioned in the presentation, about the AC copper losses in JMAG.
I think we do still have a few questions that are left answered. Just to let you know that this webinar was recorded, and we will post it probably on YouTube in the coming weeks. Also, yeah, if you want to try Simba, just go on simba.io. If you have any questions, feel free to contact us. I think we will be very pleased to talk to you about your issues and challenges. Other than that, yeah, we wish you a very nice day. Thank you again for attending this webinar. We had kind of a good crowd. That was a very nice presentation from Guillaume. So thank you all again for